Welcome to the Xilinx Power Estimator Quick Take video. In this video, we will demonstrate the capabilities of XPE and help you get started with this tool. XPE is a spreadsheet-based power estimator tool that helps you estimate power at the post or pre-implementation stages of a design. XPE provides power estimates based on the design inputs, and this helps with effective board design and thermal planning. XPE is widely used for architectural evaluation, device selection, power supply planning, and thermal modeling. XPE can be used in the post-implementation phase to do what-if analysis for such cases where XPE can receive utilization information from the Vivado report power tool. Once the data is imported, you can experiment on your design without actually re-implementing the design. Power consumption of an FPGA is divided into static, dynamic, transceiver, and I/O categories. XPE provides power estimates for static, dynamic, transceiver, and I/O power categories. Power consumption is dependent on design and is affected by switching frequency, design density, design activity rate, number of design elements, and supply voltage. Let us get started with a quick tour on how to set up the tool. Setting up XPE requires two distinct steps. The first step consists of configuring the physical attributes such as device, temperature grade, speed grade, and environment variables. The second step consists of describing a design in terms of its components. Let's look at each of these steps. Now, the first step is to pick the right device and package in XPE. Please pay careful attention to the temperature grade and process settings. The temperature setting determines the device's operating range and also influences the maximum static power. The process tab will help you determine the worst case power and typical case power changes due to manufacturing process variations. Once you set the device portion, the next step is to configure the environment to accurately reflect your actual device setup. Some key settings include the ambient temperature in which the device would be operating, the airflow that would be available for the device, heatsink selection along with board selection. These settings could also be overridden with specifying the junction temperature directly. There are also advanced settings available in XPE to model thermal resistance and to perform what-if analysis based on customized thermal profiles. Now that we have set up the physical attributes, let us move on to specifying the design characteristics in XPE. The first tab that we notice in the XPE tool is the clock tab. We will navigate to the clock tab and you will notice immediately that the tool provides for various data inputs corresponding to different clock parameters. XPE takes into account the power savings expected from the UltraScale segmented clock architecture. In this example, we will look at an example instantiation with 7 global clocks and utilizing 22% of the total clock buffers. There are tool tips for each of the fields if more information is required. We will go ahead and set up the example. We will input the fan-out number in the fan-out column. We will select the right clock buffer along with the clock buffer enable rate and slice clock enable rate. We will set the right clock frequency. As you can notice, there is a single power rail of interest for the UltraScale clock, and that is the core voltage rail. On the top, you can also notice the utilization percentage for this example. Now, let us navigate to the logic tab. In this example, we will look at an example instantiation with 300K LUTs, 500K registers, and 50K shift registers running at 500 MHz with a 20% toggle rate. We will go ahead and set up the example. We will input the number of LUTs, registers, and shift registers in the respective columns. We will select the right clock frequency along with the right toggle rate. We will also set the right fan out. As you can notice, there is a single power rail of interest for the UltraScale logic block, and that is the core voltage rail. On the top, you can also notice the utilization percentage for this example. Now that we have looked at clock and logic, let us move on to evaluate the I/O power savings. In this example, we will look at an example instantiation for 4 DDR4 interfaces running at 2400 megabits per second with data width set to 32 bits and DCI termination of 40 ohms with address width set to 16 bits and read-write percentages set to 50%. We will go ahead and set up the example. We will input the read-write percentages and data width, and we will also set the write address width. Once you click on the Create button, XPE will automatically populate the right I/O standards required to support DDR4 implementation. As you can notice, there are 9 power rails of interest for the UltraScale I/O interfaces. On the top, you can also notice the utilization percentage for this example. Now let us look at how to estimate power for the BRAM using the Xilinx Power Estimator tool. In this example, we will look at a true dual port BRAM running at 300 MHz with a 50% toggle rate and a 50% enable rate. You will also notice that XPE allows for cascade group size setting. There are tooltips for each of these fields if more information is required. We will input the number of BRAMs in the block RAM column. We will input the cascade setting in the cascade group size column. We will select the write mode along with toggle rate and enable rates. We will also set the write clock frequency, bit width, and write mode. Repeating the settings for port B. As you can notice, there are 2 power rails of interest for the UltraScale BRAM, and these are the core voltage rail and block RAM voltage rail. On the top, you can also notice the utilization percentage for this example. Now let us look at how to estimate power for the DSP by navigating to the DSP tab. We get the power savings for free from the architectural enhancements and do not need to enable any special inputs for the DSP. In this example, we will be looking at a 1200 DSP slice design with the pre-adder, multiplier and accumulator enabled and running at 300 MHz. This DSP is running at a 25% toggle rate. We will input the number of DSPs in the DSP slice column. We will select the write mode along with the toggle rate and enable rates. We will set the write clock frequency. As you can notice, there is a single power rail of interest for the UltraScale DSP, and that is the core voltage rail. Let us finally look at the transceiver power estimation by navigating to the GTY tab. In this example, we look at a 16-channel GTY design in LPM mode with a data rate of 25 gigabits per second with a data path setting of 40 bits with data mode set to raw. There are also additional customization options for each of these fields. We will go ahead and set up the example. We will input the number of channels in the GTY channels column. We will select the write mode along with the write data rate. We will also set up the data path and the data mode. As you can notice, there are 4 power rails of interest for the UltraScale transceiver, and they are VCC int, MGT VCC aux, MGT AVCC, and MGT AVTT. On the top, you will also notice the utilization percentage for this example along with the power planes required to support the GTY channels. Lastly, XPE also allows for estimating power for interlaken blocks, and one could do that by using the hard IP tab and providing data inputs for the number of interlaken blocks being used. If you have a problem with your power or thermal budget, there are many things you could consider. Determine which components in your design are using the most power. Try to use as much of the UltraScale power saving features as possible, such as BRAM cascade, LPM mode for transceivers, and fine grained clock gating. You could also review the power optimization section in the UG 997 Vivado Power Guide. You could also evaluate your activity rates and reduce excess signal power or excess device utilization. You could consider Vivado power optimization and also reduce excess static power. The external environment also could be adjusted to reduce static power. You could also review the thermal models and perform advanced thermal analysis by using the compact thermal models provided by Xilinx. In summary, accurate power calculation at an early stage in the design cycle will result in fewer problems later. The Xilinx Power Estimator spreadsheet and Vivado report power could be used for estimating the power consumption and junction temperature for all Xilinx UltraScale devices. XPE supports all the great power saving features available in UltraScale devices. Thanks for watching.